This is how I would write a test question. We work at an iPhone factory. Great job, right? Our factory is the major contributor to Apple for all their products. That's kind of key to the question. Lately, there has been concern from Apple that too many of our iPhones are defective. Through strict auditing, we know that, let's put this, let's do it this way. All right, let's change it to this. 98% of our iPhones work. Okay, so here's what we have going on right here. That is a real word. Amazing what the word recognizes. Does everyone understand what's going on right here in this problem? Does this problem kind of make sense to you theoretically? We work at an iPhone factory. Our factory is the major contributor to Apple for all their products. Lately, there has been concern from Apple that too many of our iPhones are defective. Through strict auditing, we know that 98% of our iPhones work. I don't know what, oh, when I corrected it. When Apple comes to test our iPhones, they will sample 600 of them. So let's look at what's going on right here. When Apple tests our phone, what are they going to do? Like, what's going to be the result? What data are they going to collect? They're going to collect, say, you said it, categorical. They're going to figure out if it was defective or not defective. Does everyone see how that is categorical? Defective, not defective. So that automatically should clue you in on some of the stuff we're going to be doing here. First of all, we need to figure out the three conditions. Condition number one, random. So truthfully, it'll take a random sample. There we go. The problem states that they will take a random sample. This is the first thing we usually do is check all three conditions. Nice job online. We check all three conditions to make sure they are met. If all three conditions are met, that means we will know not only the mean, but the standard deviation and also the shape of the sampling distribution. Does that make sense? And let's talk about here. So one, we need that they have to be random. Two, they got it online, less than 10%. And you could say 10% or less than 10%. You just need to be specific when you give this last part here that it's less than 10%. And does this seem to be met right here? We are the major contributor to Apple. Do you think we make, well, let's give a number that would kind of help with this. What number for less than 10% would be a good number to give? Like, would be a strong, online, try to type a strong definition, or try to type a strong answer right now if you're watching this video. Try to give a strong answer on why we meet the 10% condition. It is likely, nice job, that we make more than 6,000, thus 600 is less than 10% of all our iPhones. This is a stellar answer right here. You really only need 1-2 sentences max, but it's likely that we make more than 6,000 iPhones, thus 600 is less than 10% of all our phones. Once again, this is the less than 10% condition. And review the videos if you want to know why it's less than 10%, or accept it right now. But it's less than 10%. Less than 10%. Any questions here? Question, go ahead. 6,000, think about it. If we take 600 and times it by 10, that'll be 6,000. Now that's important to us because what's 10% of 6,000? 600. So as long as there's more than 6,000 iPhones made, 600 would be less than 10%. Because it's kind of like, maybe we work for, let's say we work for a little company and we're like a minor contributor. then you might be scared. You might be like, maybe our company only makes like 4,000 iPhones. And then 600 out of 4,000 would not be, we can figure out here, if I said something like our company makes 4,000 iPhones a year and we want to see if this year's iPhones meet the quality that they're looking for. If the problem said that, which it doesn't, we would have 600 divided by 4,000, and you see that's more than 10%. That would be a problem. But since I said we're a major contributor and these are iPhones, probably safe to assume that we make more than 6,000. The problem could say that we supply millions of iPhones a year. And then you'd be like, okay, it says we supply millions. 600 is less than 10% of a million or so. So it's safe to assume there. Less than 400 would need to be sampled. And that's very true. Nice. Will said, in this instance, if our population was 4,000 in just a fake theoretical problem, our sample size would be less than 400 or less, sample less than 10%. Don't worry if it's exactly, we'll never throw a problem at you that gets that nitpicky. The final question right here. This is where we pause, always take a breather. You identified at the start of this, I can barely see you. No, you're fine, don't worry. It's me not being able to look over. You identified at the start of this that this was categorical. Now that's key to figuring out the third condition. The third condition here, since it's categorical online, is knocking it out of the park. It's the success-failure condition. And what does the success-failure condition mean? So we need to solve NP, which is more like NP like this, equals, nope. NP equals 0.98, or let's do N first. 600 times 0.98 equals, and that's going to equal 588, I believe. And let me decrease font size here and make it look nicer. Oh, that sounds good. And then NQ. Does everyone see how I know what NQ is? Because if P is 0.98, Q is going to be what? If P is 0.98, Q is bingo. P and Q are complements. And you actually don't need to do the math. One quick way to check to make sure you've done this properly. Nice job online. One quick way to make sure you've done this properly is to make sure NP and NQ add up to N. Because you expect this many successes, you expect this many failures, and then that would be everything. Things will either be successes or failures. So 588 plus 12 is 600. So you will see, because this is 100%, 98%, 2% add up to 100%, so you get 100% of N. So we pass this right here, we are fine. What does it mean to pass all three conditions? We now know the mean, the standard deviation, and the shape. And this applies to the next chapter. And it's normal. That's a huge key thing. It will be normal. Big key thing right there. So the first thing we usually do with this is to ask you to check conditions. Remember, random, 10%, pause, and then figure out what it is. We knew this was success failure because when you collect data on an iPhone, you take the iPhone and you figure out that's Batman. And then you figure out if the iPhone is defective. So you do that right there. When you collect data on if it's defective, it's a yes-no type of response. It's was it defective or not defective? So that would be categorical in nature. So the next thing we could ask, let's go down here and we can do, let's make this all kind of purdy right here. I don't know why I keep saying it that way. So the next question asks, given the information above, or given the conditions are met. I'm just adding that in as a Brian Stevensism. So this is a dead giveaway right here. The shape of the sampling distribution of the sample proportion, or not even the shape, but sampling distribution of the sample proportion. If you see this, you are definitely dealing with P, P hat, and stuff like that, and you are dealing with the success-failure condition. This question does not say it, but if it said mean, that would be Y bar, mu, and large enough N. So if you see any of these dead giveaways, also, if you see percentages, I can't promise, but usually that means proportions. Does that make sense? Because it's like the percent that meet this categorical definition. So when you see percentages, that usually goes hand in hand with the sampling distribution of the sample proportion. Does that make sense? So let's continue on. Let's do this right here. So we need to do the formulas. We have that, and let's go to insert. Let's make this all nice. We have that the mean for the distribution you can do super cool things right here. Where's my equation writer stuff? When I go in here, P and design. Here we go. This is overkill, everybody. But I'm OCD. And here we go, our accent. And once I get in there, I can copy paste it if I want. The mean for the distribution of the sample proportion is equal to, well, I mean, if 98% of our iPhones are good, 98%, right? If you sample 600 iPhones, what percent would you expect to be good? 98%. That's all it is. So it's just like, if I tell you, we expect 98% of iPhones to be good, and you go out and you take a sample, what would you expect? And this is the expected value, or the mean, for the distribution of the sample proportion. You would expect it to equal the mean, because that's what I just told you. It's like 98% are good. Well, I expect 98% to be good. How about, and this is where our copy paste works, how about the standard deviation? Thank you. P times Q over N squared root. I bet they're saying it online. Oh, nice job. 5 points to both of you. Sequoia and up here in front, extra credit. Nice job. I love it. P times, it's not that hard to memorize, is it? P times Q over N squared root. So let's go ahead and put that in here so everyone can see we're making things perfect today. And equation, not that hard to do. Whoops, uh-oh. Something popped up and I clicked it. Okay, let me grab this, put it all the way over here. So what happens when we try to go all star on this? Equation and design and do the radical first and then do this. Nope. Can you not? Wait, oh, I was up there. P times Q over N square root. So let's put it here, P times Q over N and square root. I put it there because sometimes people hear me say P times Q over N square root, and they think we're saying square root of N or something like that, but this is the way it should look. Don't do it, but you can do PQ square root over N square root. It's mathematically equivalent, but I like it this way. I don't know. It's the way I remember P times Q over N square root. And so now this right here, we're gonna take and steal from this. Let's write it out. Let's go ahead and put in here 0.98. Doesn't matter which order we put it in. 0.98 times 0.02, and then we put that over 600, and this is equal to about 0.006. What is it equal to? 5.7? There we go. So it's equal to, nice job onliners and everyone. It's so catchy. I love it. Great job working through with the work. I love it. So this is our mean and standard deviation. Next, we need to know the shape. It's normal. Nice and easy. The shape of it has to be normal. Question? We haven't. Well, bimodal, uniform. If it'll be, we never asked this on tests, but if it's not normal, it'll be skewed. And I'll show that just briefly here as an addendum. Never hurts to show something. If we don't meet the success failure condition, especially, Matt Bogner of the University of Iowa has some really great applets. He rivals the David M. Lanes, and there's his dog apparently, or that's Matt Bogner. It's really impressive he's his dog. So here we are with the shape of the distribution, and does that look normal to you? Yeah. And I know this has a different mean and standard deviation, but look, 588 is the number of successes we expected. Check this out. You told me 0.0057, and you don't need to know this stuff. This is a little extended, tiny little tidbits. But 0.0057, right? And if you times that by 600, what do you get? Do you see it? You get the standard deviation right there. Now, here's the thing. If we don't meet the success failure condition, because now there would only be 6 expected successes, do you see it's more skewed? Now watch this. Do you see if it's even more skewed? Do you see the skew right there, that it gets even more skewed when we don't meet the success failure condition? Because now there's only 0.6 expected failures and 599.4 expected successes. And this can be easily seen if you use the sample size of like 100 and do something like 10 where that's normal, and then you do 1 and it's not normal. But do you see it becoming more normal as there's more expected successes? So very quickly, if it's not normal, it will be skewed. But when you meet all 3 conditions, it is normal enough for us to use the empirical rules. And that's why we do it. Really good kind of quick question right there. Good stuff. It's so you guys probably see it when it comes down, and that's how I like randomly click it by accident. So actually, I think I should know quicker ways. Okay. So that gets us through that. We now have the conditions being met. Also going through this, we identified some key portions of this problem. We have identified P, we have identified Q, we have identified N. That's pretty much everything till we get to the next part of the problem. Three exclamation points, you know, for posterity. What does P hat mean again? Perfect question and perfect time. So now we ask this right here. Uh-oh. So now think about this. They are going to take a sample and they're going to see if in their sample 95% are working. 95% is now a what? Because they're going to see if in a sample they observe 95%. Careful. So would we expect 95% because they're going to see if they see that? No. We still expect what? So they're seeing if, because is it possible, just tell me, is it possible that they could observe 95% are working or less than? Is that possible? How would we find out if that's probable? We probably need to look at the z-score of it, right? And then if it's outside of -2 or +2, we'll have something that doesn't seem that possible to us because it would only occur about 5% of the time or less. It depends. It's such a, like 2 and 3 are almost subjective matters. Things outside of -2 and +2 would occur 5% of the time or less. Things outside of -3 and +3 would occur less than 0.3% of the time. Moving forward in the class, we will often talk about p-values and have the 0.05 rule. Has anyone heard of 0.05 before? And that's when we'll start talking about 2 standard deviations a lot. 3 is very odd, 2 is kind of odd, depending on how you define it. And I think especially, I think on the practice test, it talks about 2 standard deviations, doesn't it? I think it does. It says like this is outside of 2 standard deviations. And had 3? Man, that's confusing, isn't it? Just understand that 2 is kind of odd and 3 is very odd. And usually on the test, we try to make it clear. And you'll see in this example problem if it's odd or not odd. It'll be pretty easy to see. And I think it should be accepted either way if people use the subjective nature of 2 or 3. It's just that 2 is odd, 3 is very odd, and 4 is ridiculously odd, 5 is insanely odd, 6 is no way could that possibly happen by random chance. Just the further standard deviations you go, the less likely it is to happen by random chance, given that the mean is actually this. So that's what we're going to look at here, and that's a really great question. 5 points extra credit, great question. And what is this 95% though? Because they're going to see if they see that in a sample. They're going to see if they see that in a sample. (95) is p hat. P hat because, oops, that's not right. Go one more way. Jeez. There we go. 95 is p hat because when you think about it, what you're doing is you're saying in a sample, might we view 95%? What's the truth again? 98. So what should they see? What should they see around? I shouldn't say they have to see this, but what's the most likely thing for them to see in a sample? 98. Now we need to figure out how odd 95% is by doing what? Finding its z-score. And the very first thing I would do, and so few people do this, I'm going to put it here. Let's say this. Let's do this. Draw the sampling distribution of the sample proportion. It's not that hard. I'll do it on the screen very quickly, and then I'll show you. Online won't be able to see this, but you'll see it in seconds. You would simply draw a normal curve, because we stated it's normal, put it at the center, 0.98, and then you go down 3 standard deviations, you go up 3 standard deviations, try it yourself, and then you simply subtract the, that's a 7 now. You won't have to put up with my horrible handwriting in a moment. And then this is 0.968 and 0.962. And so you don't have to put up with my horrible handwriting because no one wants to. That's just to prove we could do it. We can go over to the David M. Lane applet. Now, once again, you would say to me, Brian, we don't have this on the test. But did I make it clear that I simply could have written 0.98 at the center and then went up and down the standard deviation? And I always hate it does it where it doesn't give the last number sometimes. This is good enough here. It's rounded. It'll give us an idea. Are these the same numbers I wrote out just a second ago? Yep. And so you could draw this yourself is the key. The reason I just did a very quick sketch was to say, yes, I'm using the David M. Lane applet. Yes, you do not have access to this on the test, but all you're doing is putting in your mean and then going up and down the standard deviations. And I rounded it for the moment. It's going to make it look nicer, and it's going to show us something that's going to be very easy to see. So this is what you would draw out, and you can just draw this out, put in your mean, go up and down the standard deviations. So with this in mind right here, can you almost see the z-score? What's the z-score about? It's very close to. Very close to what? -5, yeah. Because check it out. 98, 974, 968, 962. What would come next? Oh, nice job, Catherine. 5 points, Catherine. What comes next after 962 if we're subtracting 0.006? 956, then what comes next? 950, which is 95. Does that make sense? Now, this is not exact because I rounded it. So how do we figure out the exact? Well, let's go ahead and calculate the z-score. The z-score for this is going to be the formula. Nice. Thank you, onliners, for typing it out. Good job. Good practice. Good recall. Do you have it? I always do that. I always say observed minus expected over standard deviation. And you just have to think, what did you observe? You have to kind of break it down and be like, okay, we need to do observed, which is, I have to cheat up here, I have to go grab it. We observe in a sample p hat. Does that make sense? We're going to observe in a sample p hat because that's down here. Look at what's at the center is p. Go ahead. No, you don't have to write these equations. This is just me going above and beyond for viewing purposes. How did this extra bar occur? Well, we might just have to put up with that. Whoops. I was trying to just select everything inside of here. Well, sorry about that bar right there. What? Oh, it has to be something down here at the bottom, doesn't it? Okay, let's try. What? Oh, I'm underlining. It must be it, right? Or not? There we go. That was weird. Okay, so I didn't know I hit that. Okay, so now we have p hat minus p over the standard deviation of p hat. And we simply plug and chug into this problem. In our sample, we observed, say it again, we observed 0.95. And then we would say we subtract the mean because all we're doing is getting a distance up here. Does that make sense? How far away is 0.98 from 0.95? And it's below. So this will turn out negative on top. And then on the bottom, we simply have 0.0057. And this equals, a few people have done it already. Thank you, people who have done it. We have down here, we have negative 5.26. Just if you solve it, negative 5.26. And the reason we graph it out, I want to make this clear, is because if you graph it out, then the answer you get should look something like it. Did we get about 5 when we graphed it out? We rounded the numbers, so I'm not going to get an exact answer. But we got about 5 trying to figure out, oh, 4, 5. We can also see the problem could just say, is this unusual? And your drawing shows that it's more than 3 standard deviations away, or 2. I'm fine with either answer. But it's very unusual. We try to make it very obvious with these problems. We don't want to give you something that's like 2.1, because that's like, it's kind of unusual. I mean, I'd love it, especially in advanced classes. I'd want you to say things like that. You'd be like, this is kind of unusual, but not very extreme. You know, this could happen. And then you could actually give the probability. It'd be close to 2.5% of the time, because it's a little bit less than 2, so a little bit less than 2.5. But this, is this going to happen down here, all the way down here at 0.95? Do we have anything to fear, really? No. You have just walked through a whole example problem going over 15.1 using the sampling distribution of this sample proportion. Now, I want to make something clear right here. This is a theoretical distribution. And one of the things on the review sheet talks about this. If you go out and sample one iPhone, the probability it'll be defective is 98%, or probability to be good is 98%. If you were to go out and sample 600 iPhones, you would get one random dot inside of here. Does that make sense? So this is repeated samples of 600, where you're sampling just a random 600 iPhones. Like, it could land here. And look at this. This is around 1 standard deviation below, so that seems very possible. It could land here. It could land here. It could land over there. But the more probable things are inside of here, as in 68% of the time when we go out and sample 600 iPhones, we will see that 97.4 to 98.6 of them are, 98.6% of them are working. Does that make sense? This is when we go out and sample 600 iPhones, the theoretical distribution of what we expect to see. And the most likely thing to see, not that we will see it, but the most likely percent to see is what? 98%, because I told you 98% are good, and if that's the truth, which we're assuming it is, then we'd probably see 98% or something close to it. And what is something close? It is defined by the standard deviation. Does this example problem make sense? Questions if you have them, because we're going to go on to the next part. I keep thinking of pulling a trick question, like doing another distribution of the sample proportion, and then you guys are all ready and start answering it the wrong way. I'm like, no, it's still sample proportion. Like, if we want to see if people are satisfied with their iPhones, is that proportions or means? And we ask them yes, no. Proportions, like the percentage of customers that report that they are satisfied with their iPhones is believed to be 75%. We want to see if with the new iPhone, if we're still meeting that, we sample 400, yada, yada. Does that make sense? So you could change it. Remember, every question you ask with these types of 15.1 problems have to be categorical questions. Are you satisfied with your iPhone, yes or no? If it said, give a rating of your iPhone 1 to 10, that would be quantitative. If it said, how long does your iPhone last, that would be quantitative. If it said, it is believed that only 4% of people get special edition iPhones, is that quantitative or categorical? It is believed, or here we go. iPhone has data that suggests, or no, Apple knows that only 4% of their people get special edition iPhones. So then we're going to come up with a distribution and all that. Would this be a categorical or quantitative? And online's getting it. Categorical, because then you're going to say, do you have a special edition or not? It is believed that only, or Apple knows that only 40% of their customers are using the latest iPhones. Categorical or quantitative? Categorical, because are you using the latest iPhone or not? Apple knows that on average, people take, and not even that I say average, but Apple knows that the life of an iPhone for most people, the average life of an iPhone is 5.5 years. See, I can't even not say average when I do these types of questions, but be careful. Well, don't be too careful. The average life of an iPhone is 5.5 years. What is that? Quantitative, because how many years did your iPhone last? So do you see these little switches I'm doing right here where I'm giving a quantitative question to start? Just like always look at the question and be like, how long did my iPhone last is what they're collecting on. That's quantitative. And that will bring you down a road for the equations you'll use and also for the conditions you'll talk about. So important to know if you're doing a quantitative or categorical question. So let's do a quantitative one here. The auditors. The evil auditors. are not satisfied. Can't spell. The auditors not satisfied. The auditors are not satisfied. They decide to do a stress test on our iPhones. We know from our own data that the mean or the average, the mean force it takes to break our iPhones is 30. What is Newton's? Is it Newton's is force, but how do you abbreviate it? It's N, just capital N. So, nice job. You guys know this better than me. With a standard of, let's say, 12. The distribution of when they break due to the force is lightly skewed. They will sample, changing it to 15. Okay, so let's check the conditions to see if we can model this. The first thing could be, can we, let's see, do we meet the conditions? So do we meet the condition for the sampling distribution of the sample mean? Question mark. Thank you, Word. Condition 1! Random. So I got to update my question here. It doesn't say random, so watch out if it doesn't. Stop it. I want it to do, now it's like, oh, you want me to autocorrect? Not autocorrecting. Thank you. So they'll randomly sample 25 of our iPhones. So now we do meet it. Random problem states the sample was random. That's one of the easiest ones. But once again, please do not lose points on it. One test, we did have people lose points because they didn't see that we said we never said it was random. So make sure you see that it is random in there. I will fight tooth and nail if we don't say random. Like if we just, no, I know my Pearson. This is the one thing. My Pearson will sometimes not say it's random, right? And they're like, you can assume it's random. I'm like, oh, come on, my Pearson. But on our test, if it says random, it's random. If it doesn't, question it. And I think sometimes we've even put like the maybe in the middle. But make sure it says random. If it says random, you're good. You're done. Easiest condition to do. Problem states that it is random. Random, 10%, and then wait for the third. So they're only sampling 25. What? It's probably your A+ answer right there. Usually I go through and just give the X. Oh, slow down, Catherine. Slow down, slow down, slow down, slow down. Too close. It's large enough. And a few ways you'll see. One, it's large enough if you're given the mean and the standard deviation. If you're given an actual mean and standard deviation related to quantitative data like quantitative mean, quantitative standard deviation, you'll also be given the shape of the distribution. So I said that this is lightly skewed. If it's lightly skewed, don't worry, it's good. You were thinking you're paying attention, Catherine. I'm throwing you 5 times extra credit. Like it, correct yourself, that's great. So when we see right here that it's large enough, we need to take a look at what's going on. So large enough condition is the following. When we have a distribution that is normal, let's look at this again because it's going in the video. Hello, video people. So let's go over here to the central limit theorem applet. Central limit theorem applet. And here we are. If our original distribution is normal, then a sample size of even 2, as in you take 2 observations and average them together, 2 observations and average them together, 2 observations and average them together, and you keep doing that, the new distribution will still be what? Normal, but let's say it's skewed. and I learned something. I learned how to use this even better. If it's skewed and we were to take a sample size of 2, here's how the sample size of 2 would look. It looked like that. Oh, and I didn't do this. Dang it. I do know how to do this, I promise. So there's a sample size of 2, but then a sample size of 25. How do you get the distribution of means of sample size 25? You have to do what? Take 25 observations and average them together. Now, which of these did you notice is closer to the mean? This one here or this one here? The mean is this blue line right here. The second one, right? Do you think that's by chance? Well, if you take a whole bunch of observations, aren't they all going to kind of average out usually? And then you'll get a tighter and more normal distribution, where the distribution of the sample size of 2 still looks pretty skewed, right? This is with repeated trials. But the distribution of sample size 25 is tighter by a factor of the square root of n and is more normal. To exemplify this right here, let's go ahead and do one more custom distribution. And let's do the classic where we make a standard deviation of something like 5, which I'll try my darndest. It's in the video. There we go. Now check this out. The new distribution for the distribution of sample means of sample size 25 should be what? The new standard deviation should be what? Why did I pick 5? Because the new standard deviation will be, and this said online, nice job, will be 1. Check it out. There it is. It's 1 right there. Also, my distribution has a pretty weird skew to it. Since this is kind of heavily skewed, and the problem will state it, it would say there's a strong skew. Since there's a strong skew, is 25 large enough? No. If there is no skew, if it's normal, what's large enough? If it's normal, what's large enough? If it's kind of skewed, what's large enough? 25, they said 1 for the first one. And if it's heavily skewed, what do you need? 100. And so this is maybe a heavy skew. I know the other one maybe looked a little more skewed. Don't worry, the problem will describe to you. It is normal, lightly skewed, or heavily skewed. So 100 can pretty much take care of everything, and we could go more in depth in other classes, which if you want, we will. But 100 takes care of the strongest of skews usually. And how does ours look? Ours is what kind of skewed here? Lightly. So the condition is large enough n condition. And since there you go. Since our distribution is only lightly skewed, the sample size of 25 is large enough. If it had said it has a strong skew or heavy skew or extreme skew, some of those big scary words, it would need to be a sample size of 100. And we've also seen some key concepts here because the next question I'm going to ask, I think like everyone's doing all right. The next question being here would be, what is the, I keep hitting the wrong button. Let's just do this. Let's go up here. We have it all nice and perfect. Given the conditions are met, which they are, what will be the mean, standard deviation, and the shape of the sampling distribution of the sample mean? So let's go ahead and steal. Bring it down here. We need to do some changes in here, so do not pause the video here, whatever you do, and start writing things down. These are very wrong answers. So let's go ahead and do changes. And where's my bar? For the longest time, I did not know you could do this in Word. And I was like, what? I was like Googling online, like Y bar, and no one had Y bar. So check it out. The mean for the distribution of the sample mean will be the mean. As in, if we expect our iPhone to break around 30 newtons, does that make sense? If I take 25 iPhones, what should they break on average? Around what? Does that make sense? If you take all, like our iPhones at our factory usually break around 30 newtons. That's like where they average break on average. So if I take 30 of my iPhones and then I average them out, like I figure out what they break on average by going back here and looking at again, what we're literally gonna do is take 30 of our iPhones. Let's turn this one off here. Pretend this is 30. And actually I said it was normal. No, I said it was lightly skewed. We'll put this. Don't worry, we'll pretend that's slightly skewed. So I'm gonna take 30 iPhones and then take the average of them. Does that make sense? Could it have been any random 30 iPhones they took? Is this another 30 iPhones? I know it says 25, we're pretending it's 30, but I can't change this to 30. Could they take any random 30 iPhones? They could, right? This is a theoretical distribution down here of what could happen. And do you see how it's tighter and more normal? That is the central limit theorem. And that's why we want the conditions to apply, because we can use the empirical rule once again. And I know it says 25, but we're pretending it says 30 because I can't change that.
I thought that the sample was 25 and we're seeing how much.
Well, so each single iPhone, which would be up here, each individual iPhone, and pretend this says like 30 in our numbers, I just can't change them. Each individual iPhone will break on average around 30. Like in the long run, our iPhones break around 30. Does that make sense? And there is a standard deviation to it of, I believe, 15 or so. And it's skewed, so that's probably why. Because it doesn't work if you do 68, 95, 99.7. But with this right here, we're now saying they're gonna take a sample of 30 of our iPhones. Is that right? 25. Our problem is 25 also. Were they saying that online? I was saying 30, but I got mixed up in the head because of the 30 is the mean. So sorry about that for those watching. My brain, as I make up the problem and try to solve it, I reversed a number. But we do have a sample size of 25, right? So once again, what we're doing, for those who are at 30, I was wrong, we're taking 25 random iPhones. Does that make sense? And then what do we do? It's easier to see if I don't have the bottom distribution there. We're averaging them together. That blue dot you see is the average breaking strength of those iPhones. Does that make sense? So they could take any random 30 iPhones. But this new distribution will be two things: tighter by a factor of the square root of n, and it'll also be more normal. And it's normal enough because we have it. Let me see if the chat's moving down. I feel like, no, it is. So going back to here, when we check the conditions, the mean for the distribution of the sample mean is equal to the mean, as in if one phone required 30 newtons to break, we'd expect this phone, like the average of 25 phones to be 35 newtons. Just like when we talk about if one guy is 5'9" on average, if you take 25 random guys, what do you expect their heights to average to? If one guy is 5'9", if you were to take 25 guys and average their heights, what do you think it would be? 5'9". Probably your best guess, right? It doesn't have to be 5'9", but it would be the mean is equal to the mean for the distribution of the sample mean. So if you take a sample of 25, you'd expect it to be the mean still. So that's what we have going on right here. Next, we need to do the standard deviation for the distribution of the sample mean. And let's put it in right here. And now we need to do some slight modifications to this. Not too much. Let's insert an equation. And let's do it. Equation editor. Thought I clicked it. There we go. And here we are. So we need to take our original standard deviation of sigma, which is there no sigma today? There's no sigma. Help me if you see sigma. I usually know where it's near. I think it's around here, isn't it? Here we are. Do you guys see sigma? Did we pass it? Did we pass it? I want to put in the right symbols. Always nice to make it look nice and perfect. You need to go to Greek, right? Oh, more? Where's my Greek people at? Do people really need all these symbols? Sorry, let me go to, there's Greek in here, right? Greek, here it is. Greek extended? Latin extended, okay. This is well-used class time. Well, that's not it. It has to be right in here. We'll give this another 4 seconds if we don't find it. I'll just write.
Yeah, there's another Greek at the top.
There's another Greek all the way at the top of it? Oh, it's just regular Greek old, right? Yeah. All right, here we are. There it is. Yeah. So it's just like hidden in there. Sorry, that was the most fun we've ever had, right? And they've already written it online. The standard deviation of the square root of n. They've already got it. Thank you guys for putting up with me. I should have just went to, you can just go to Google and just type sigma symbol and it'll give it to you. So now the original standard deviation was 15. Oh, it was 12? No, I changed it, sorry. Because why did I change it? Tell me why I changed it. To make it easy. Because now I think we can all solve that. It's 15 over 5, which is 3. That's nice and neat. Does that make sense? The shape will still be normal. Just we're writing everything out here nice and neat. So if you want to pause while you're doing this right here, that's the biggest thing. I want people to be able to pause this video, take a look at this, understand that we're saying the standard deviation for when we take sample means, this is the distribution of the sample mean, the sampling distribution of the sample mean, will be 3 because we take the original standard deviation and divide it by the square root of n. The new mean for the distribution of the sample means will still be 30 because if we expect one iPhone to break at 30 newtons, well, on average, 25 iPhones should break around 30 also. So the new distribution has the same mean, it's tighter and more normal. Does that make sense? 3 big things right there. So the shape is still normal. This is due to the large enough condition, yes. And it wasn't normal to begin with. It was lightly skewed. The large enough condition, once again, states that if it's normal, it'll be normal. When we increase n, it'll just get more tighter. If it's lightly skewed, little light skew there, like I'm trying to show a histogram being lightly skewed, then the sample size needs to be 25 or greater for it to be normal. And if it's heavily skewed, then it needs to be around 100. Do you see how I really have to move my arms when I do heavy skew? I have to move my arms all like this. But if I do light skew, I only have to move back a little. The bigger n is, the more it normalizes it. So that's why it's large enough. So when it's large enough to normalize it, well, if it's normal, how large does it need to be? If it's normal, 1, 2, anything, correct? If it's lightly skewed, then it needs a little help. And what's a little help? At least 25. If it's really crazy, then it needs what? At least 100. So that's what we have going on right there. So the conditions are met. Uh-oh, we better, here goes the trouble. So our iPhone factory will be shut down if they find that on average in the sample of 25, in a sample of, in the sample of 25, the iPhones broke at, let's go with 26. Is this possible? Or does this, in the test we say like, does this seem like in a rare event? Or is it possible? Or is it, everything is possible? Or is it probable? Or is it, does it seem like a rare event or not a rare event? Yes, 26 newtons, correct. Good point, 5.6 credit, thank you. Makes it a little bit clearer. So they're gonna see, this means they're gonna take 25 iPhones, they're gonna put them through the stress test, and if on average these iPhones broke at 26 or less, our factory's getting shut down. So if they break at 26 or less, because like if they break at 1, that's really bad. Is 26 newtons a lot of force? I don't know, that could be like a freight train hitting a wall for all I know, or it could be like a hammer hitting a nail. Like, that's the thing. Because one iPhone with all of this variation could easily break at that, right? This is where people get confused because one iPhone could very easily break at this. Because remember, the original distribution, which was lightly skewed, and I could have said to the right or left, but didn't really matter, had a mean of 30 and a standard deviation of 15, right? Now, this doesn't even make sense because we have negative down here, so it doesn't even work properly. Does that make sense? So we can't really model this, but even if we were to, which this is improper, I want to make that clear, it seems quite possible, and I said 26, did I? It seems like a quite probable event right here because it's very close to the mean, very likely. But let's go ahead and see if this will happen to us here, because now we're going to take the new standard deviation into observation minus mean over expected, over standard deviation, excuse me, observation minus mean over standard deviation. We're taking basically the same formula, and you can see my copy paste right here. A lot of the remainder of this class repeats itself in a good way, as in if you learn the concepts of how a z-score is done, all we're doing is standardizing a difference. What in the world? That was like the whole, oh, I think I hit like print screen really quickly. Oh my gosh, who knows what's going on? All right, so let's go ahead and take this here this time and try it. Watch it do it again. Don't go crazy, computer. There we go. So y bar, and you could write, question? It'd be how many pounds, of course? It'd be, that seems pretty weak, doesn't it? And if you drop like a 5-pound weight on your iPhone, that could shatter the screen, right? And that's broke it? Okay, good. But it depends on how you apply the force. Like if you apply it, like you could apply that like on a nail, like drop a weight on a nail on your phone, you just smash the screen. So it just depends, like, yeah. So, maybe. So this seems plausible, right? I don't know how iPhones break or, yeah, but it's working out. It's working out. So we've got, thank you, 5 points for the learn something new every day extra credit. I like it. Always try to learn something new. And there is our y bar. So we need to do our observation. We don't want to observe 26. What do we expect? 30, and then our standard deviation is 3, and I bet they solved it online. I didn't draw it this time. I probably should have. They've got it online. Nice job. Does this seem like a rare or unusual event? No. And we could even draw this out. It's negative 1.33 standard deviations below the mean because the new standard deviation is 3, and we draw it in here, and we could actually figure this out. So now I want you to figure out the probability of this happening and give me an estimate. I want you to use the empirical rule. Using the empirical rule, figure out a probability, and I cheated by drawing it for you. Makes it a little too easy. We like too easy though, right? Yeah, yes, good. Where can I gain back room? I guess I could delete it. No! Really? Should have enough room now. Dang it. So if you're trying to figure out the error right now, I'll give the answer in a half second. I'll zoom into this so you can see it better. So here we are right here, and they might have the answers online. It's between, careful, close, Will. You got one answer right. Does anyone else have another guess right here that this area is contained between what and what? 16 and 2.5. And why is it 16 and 2.5? Is because between here and here is how much? Tell me how much area I'm containing. And that's where I say 68. Let's do the outside. Outside is what? 32, and then what's one of my hands worth? 16. That means there's 16% below here. Inside here and here is how much? 95. Then outside of that is what? 5. Then one of my hands is worth 2.5. 2.5 from here down is too little, and 16 from here down is too much. So 2.5 and 16. No worries, no worries. So 2.5 to 16. I'm throwing you a 5 times extra credit. Well, I don't think I've given you one today. Great job. Great job. Once again, if you're watching the video online, that's end of the semester bonus. It's not on the test. Like, man, everyone's acing the test in Brian's class. What's going on with those grades? No, it's just end of the semester bonus when we figure out participation bonus. So we would have between 2.5 and 16% of the time. And once again, I'll show it visually here for people who want a little refresher. What you're viewing, let's go to z-scores for the moment, is between -1 and 1 is going to be around 68. Empirical rule states 68. That means outside of -1 and 1 is 30, my brain, oh, I didn't click it, is 32. So 68 inside, 32 outside, that means below -1 is going to be 16. And these are all rounded, 68, 32, 16. These are, the David M. Lim gives more exact numbers, but the empirical rule lets you hold it in your head. But then if we go to -2 and 2, so let's change all these numbers. Okay, then we have between is 95, basically. Outside is 5, basically. And then one side is 2.5. Now it is 95.449. You saw the more exact numbers, but we know the empirical rule is 68, 95, 99.7. We know the remaining empirical rule as 99.7. It is technically 99.73. So just 68.26, I think. You don't need to know the exact. When we use the empirical rule, we just use 68, 95, 99.7. But there are more exact numbers. Please do not try to memorize that for the test. There's no reason. We will only hold you to 68, 95, 99.7 for test 2. Test 3, you won't need to memorize them, but we will introduce the concept of 1.96. And look at what 1.96 solves out to. Do you see why you might have to know 1.96? Because what is 1.96? It's exactly 95. So we will learn that later, but if you know 68, 95, 99.7, you should know 1.96 later on is the exact. Don't worry about learning that now for test 2. That's just what I call future-proofing us a little bit. But 68, 95, 99.7, you're welcome, you're welcome. So just a quick review of that right there. And I always like to throw in the extra tidbits. Well, that's got it. I think we should do at least one problem now also because we have about 15 more minutes. You guys want to do at least one? So that's got that. If you want to see the video, the whole thing will be posted later, but we did the difference between 15.1 and 15.2 to kind of highlight those key differences between what you learned in each one of those sections. Just a big kind of review problem for each. But now one of the biggest things people give me is these at least one problems. They're like, Brian, there's no way. I just don't get them. Well, I'm going to bring some chocolate to the exam. Tons. You guys know me. You come to my office, I got candy. Except for as of lately, because everyone ate all the candy. There'll be more candy. Okay, I shouldn't say this. It's not my candy. You're going to go to an evil witch's house. She's evil. So the evil witch is going to have poison candy. But the probability of the candy being poison, can't type today, probability of the candy being poison, I knew it was spelled that way. I spelled it earlier and I was like, this doesn't look right. The probability of the candy being poisoned is 0.02 or 2%. That means the complement, or as we would say, the probability of the candy not being poisoned is what? 0.98. So what is going to happen? Who wants to eat some candy? How many pieces of candy are you going to take? Mind you, you don't know right now that the candies are poisoned. Does anyone want to eat some candies? How many candies did you eat? 6. Oh, they're eating 5. Catherine only ate 5. Okay, should we go with 5 or 6? Class vote, raise your hand for 5. 5 is easier. They're both easy. So we're going 5. The 6 candy eater took that. You found out on the 6 candy, the witch said, ha, they are poisoned. Horrible witch impression. But the witch said they're poisoned. It's sometimes the worse an impression is, the better it is. So the witch said they are poisoned, and you stopped right there. So you only ate 5, right? You had 6 in your hand, but you only ate 5. Now, I think we would all agree, how many poison candies do you want to eat? 0. So you're freaking out. You call it Brian Stevens, really? You call it Brian Stevens, you say, Brian Stevens, I need you to talk to me and tell me what's the probability that I did what? Wow, right there. The probability I ate at least one poison candy. Does that make sense? Because if you ate 1, that's not good. So the probability I ate at least 1, this evil witch. So we're going to do 0, 1, 2, 3, 4, 5. What do we not want to? Well, this is weird when we talk about this. Let me talk about this one. We will either have that you ate that many poison candies or this many poison candies. Does that make sense logically? You will either eat 0 or at least 1 poison candies. Does this all make sense? Now, you ask me, what is the probability I ate 1 poison candy or more, which is at least 1 poison candy? What is the probability I ate at least 1 poison candy? I think you might already see it even. What are we trying to figure out for here? We are trying to figure out, they've already got it online, they got it. I want you to explain to me what you want to have happened when you ate the candies. Let's see it. What do you want to happen? You guys are already figuring it out. 0.98, because wait, your first candy was what? Not poison, and your next was? Yep, this is exactly it. Your first was not poison, and your next was not poison, and then Brian changed the way it was configured, and your next was not poison, and your next, and your next. Does that make sense? This is what you want to happen. And I say to you, well, the probability that you ate non-poison candies was simply 0.98 to the 5th power, or as we colloquially know it, 70%? What is it? 0.98 to 5th power? Well, you already saw the whole thing. Why are we going to do 1 minus? I have no clue. Ooh, that's not bad. Eat some more candies. So the probability that none of the candies were poisoned is this. But you didn't ask me the probability of you being safe and sound. You wanted the probability that you're not safe and sound. And would you agree this is safe and sound and this is not safe and sound? When I say safe and sound and not safe and sound, what are you hearing? Safe and sound, not safe and sound. You're hearing that these two events are what of each other? Complements. You have eaten 5 candies. One of these things must be true. You have either eaten 0 or 1 or more. So the set, and I don't know what I just did there, the set of all events equals to what? If we were to add all of this up, what would it equal? If you add up all of these events, it would equal what? 1. So why don't we simply just take this event right here, bring it over, and subtract it? Does that make sense mathematically? Does that make sense? Now these are all, I've got them colored because they're events. That's not 1 minus 0. That's 1 minus you ate no poison candies. Because we can read this as, we'll read it in a second here, but this is everything but eating 0 poison candies. Does that make sense? So mathematically what we did, again, I'll show you, is we had over here everything. This is one of these things must occur. Then we said, let's go ahead and subtract off 0. So now we have everything but 0 is 1 or more. And does that make sense? 0, 1 through 5, everything but 0. What's everything but 0? 1 through 5. So it makes sense when you talk about it. And then we figured out the probability of 0 here. And let's write probability 0 poison is equal to not eating a poison candy and not eating 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 a poison candy, which is mathematically this, which turns into this. So to write it out, and we can solve the whole thing, you feel all right, don't worry, you should have had that 6 candy. We could figure that out. We have a lot of fun with this problem with some advanced solutions to it. But now we have everything but right here. And I want you to read this. I want you to be able to read these things because that's when you know you've done it properly. 0.0961. Is that correct? Good deal. So what we have here is everything but you have poison candies, 5 poison candies. I like to say the first thing, everything but the candy is, oh, sorry, I said it way wrong. Everything but the candy is not poison all 5 times. That's what I want to say. Everything but the candy is not poison all 5 times. Does that sound good? No. Like, it doesn't sound good when you say it, right? Everything but the candy was not poison all 5 times. That means it was poisoned at least once. That's the key.